Hello there, ladies and gentlemen, boys and girls. Welcome back to the Ephemeris podcast. I'm your host, Aphelion, and before I get into anything, if you happen to be a new viewer clicking on this video, I just wanted to let you know that this is an audio-only podcast. If you're on YouTube looking for visual content, that's not what I'm providing here, but I do provide my podcast episodes on Spotify, and if that's where you get your podcasts, I highly recommend going and following me there. But anyways, if you're here to stick around, then this is the Ephemeris podcast where we talk about just new things happening in astronomy by analyzing like 3 articles per week and sort of discussing them in detail. So, with that out of the way, let's get into the content of today's episode. So, the first article we have is an extremely red supermassive black hole. The second article we have is about AI in astrophysics. And the last article, we're going to return to an idea from a couple of episodes ago about gamma ray bursts. So, first story, super red massive black hole. Obviously, this kind of content, I guess, makes for the bread and butter of the podcast, because here we like to look at the extremes of the universe, and it's kind of weird to think that we started this whole thing with blue supergiants and never stopped looking at all the mind-blowing things about astronomy. So yeah, that's just another way of thanking you all for sticking around, but let's not deviate too much here. So we're taking it back to large redshifts and gravitational singularities with the new discovery of another crazy supermassive black hole. And its mass is 40 million times the mass of the sun, which is a very, very large number. And if you're a returning viewer, you know that I like to break down crazy numbers. So that's what we're going to do here. Let's start off by mentioning the fact that 40 million is the population of Canada, roundabout. It's like 41 million. So if we were to sort of draw an analogy here, if we congregated the population of Canada into one place and then made every single person as massive and as large as the sun, we would get this supermassive black hole that we're talking about, which is, I mean, every single time I do the research for these huge numbers, it blows my mind. So that's one thing. And then on top of that, this supermassive black hole came into existence only 700 million years after the Big Bang. So let's imagine that in this way. The life expectancy at birth of a human on average in the world in like 2019 was 73 years. If we scaled the age of the universe to that of a human being, 700 million years into the universe equates to 4 years of a human being's life. So this huge object with tons and tons of mass came around very, very early in the universe. But these statistics only tell part of the story. There are some other things that we know about this supermassive black hole. It's consuming a lot of gas and dust, and it's one of 3 dots that were observed by James Webb Space Telescope in a recent study. So astronomers have hypothesized that this object is a quasar, and we love quasars on this podcast. So let's talk about these details a little bit more, because, there's obviously reason behind why astronomers see these certain things and think, okay, this is what we're dealing with. Quasars are most notable for their relativistic jets, which occurs when matter in the accretion disk being transported to the poles of a black hole. They are launched at high speeds with lots of energy, which is seen in the form of light. It's a phenomena that the astronomers are attributing to the dots they see from the James Webb Space Telescope data. But with that information on its own, you'd think the light coming from the quasar should only make one of these dots. But there is more to the story here. We actually have a case of gravitational lensing on our hands. If you're not familiar with gravitational lensing, It's a phenomenon that occurs when basically an object in the universe has such strong gravity that it bends the light attempting to pass through it. And so what will happen is the light will pass around it, and it'll create some distorted imagery. And sometimes it'll cause Einstein rings, which is a bit of a different subject. But anyways, that's the description for gravitational lensing. Maybe a bit too concise. There are definitely some details that are probably left out there, but for the sake of simplicity, we'll just roll with this definition. So, in this scenario, the light coming from the quasar was gravitationally lensed by a galaxy cluster and was used to JWST's advantage, because otherwise it'd have difficulties peering that far back into the universe. Again, this object is like something like 12.9 billion light years away. It's very, very far, and James Webb Space Telescope is quite a tremendous telescope, but going all the way that far back, you do need some help. So, anyways, what happened with this lensing object that is the galaxy cluster being between us and the quasar is that the lensing object created 3 different pathways of light that were contorted, and it joined back at the point where James Webb Space Telescope observed the object. And if it's difficult to imagine what that is supposed to look like, let's put it this way. So imagine you have a field of space-time. It's kind of like a fabric, and you place James Webb Space Telescope on the close end of it, and you put the quasar way on the far side. And then you have this galaxy cluster in the middle. And what the galaxy cluster in the middle does is it actually bends the fabric of space-time, so that it kind of like droops. And so when you draw the light rays that are going from the quasar to James Webb Space Telescope, you'll see that they actually curve around the galaxy cluster, which is again drooped space-time. And so there were 3 distinct pathways for light that kind of joined together at James Webb Space Telescope. That's essentially what happened. So that's how we got the 3 dots, and so that's why astronomers were like, okay, because we have these multiple pathways of light and they're quite strong, they're in these dot forms, they're like, okay, this has to be a quasar. Because, such a dot would only occur if the light was coming from a compact region, and because of the object's color, they knew it couldn't be like anything like a star-forming galaxy. It had to be a black hole. So there's also another insightful quote from the co-lead that talks a little bit more about this observation that they've gotten from JWST. Quote, "The spectra were just mind-blowing. By combining the signal from the 3 images together with the lensing magnification, the resulting spectrum is equivalent to around 1,700 observing hours by JWST on an unlensed object, making it the deepest spectrum JWST has obtained for a single object in the early universe," unquote. So yeah, this was quite a magnificent observation, and it tells us about quite an extreme object. But there's something even more interesting. It's that we've barely understood how much of what exists in the system that we're looking at. So the numerical lensing model that astronomers use here kind of limits their ability to gauge the size of the black hole compared to the system. But even then, the black hole must make up a minimum of 1% of the system's mass, which is massive. I mean, I can't put any numbers behind it, but that is, you can tell that's a massive black hole when you hear about a fact like that. So, all of that to say, there's a lot to the story that we don't know, and it would be groundbreaking if we discover new ways to unravel the mysteries of such huge and redshifted objects, because we have this thing in cosmology and astronomy where we can't figure out whether galaxies or black holes came first in the evolution of the universe. So if we sort of figure out what's going on with systems like these, and what part of it is a black hole versus star forming matter, then that'll help us with the answer to this query that we constantly have. So that is the first story. Now our second story is going to be interesting because, believe it or not, in the year 2024, artificial intelligence is all the hype and looking to be the next big futuristic thing. And it's cool and all, but what's that got to do with astronomy and astrophysics? Well, we have an article today that has given us an answer to that, and you'll want to hear about this. So, heavy elements and metals make up an interesting portion of celestial studies. They tell us about the age and evolution of certain objects, like the observation of elements heavier than hydrogen and helium in a star, or the observation of silicon lines in type 1a supernova versus any other types of supernova. So heavy elements just help us with like spectroscopy and figuring out sort of how old certain objects are, where in their life cycle they are, stuff like that. But how the really heavy elements originate in the universe is a different query and leads us to more complicated ideas. You can have light elements like carbon, nitrogen, oxygen that can be found in a white dwarf easily. Maybe even the hottest white dwarfs will have like chromium, manganese, iron, cobalt. But after that, when you start looking at like platinum and gold, we have to start looking at greater stellar remnants. The current theory of the origin of heavy elements like this is that they come from neutron star collisions, and this event in the universe is the only one that we know of that produces conditions hot and dense enough for free neutrons to merge with atomic nuclei and form new elements in a split-second window of time. Astronomers call this process the R process, or the rapid neutron capture process, and so it'll form a lot of different isotopes, and there'll be all kinds of nucleosynthesis that occurs, but in very, very extreme conditions, so that they're like stars are able to create such heavy elements. But what holds true for all theories is that they have to be tested, right? And herein lies the problem. How can you test the viability of such a theory? It's such extreme conditions, very short time period, and all of that stuff. There are like a whole lot of different possibilities when it comes to creating these conditions and then expecting nucleosynthesis to happen. So that's where AI comes in. I will go ahead and quote the article because they've put it very well here of how AI is helping. Quote, Los Alamos National Laboratory scientists are front and center in using machine learning algorithms, an application of artificial intelligence, to successfully model the atomic masses of the entire nuclide chart, the combination of all possible protons and neutrons that defines elements and their isotopes. Many thousands of atomic nuclei that have yet to be measured may exist in nature, said Matthew Mumpower, a theoretical physicist and co-author on several recent papers detailing atomic masses research. Machine learning algorithms are very powerful, as they can find complex correlations in data, a result that theoretical nuclear physics models struggle to efficiently produce. These correlations can provide information to scientists about missing physics and can in turn be used to strengthen modern nuclear models of atomic masses. So essentially, AI here is helping us crunch all the calculations that map out all of the possible nuclides that can occur due to different types of nuclear synthesis. And, identifying all elements and isotopes that occur in nature only gets nuclear physicists so far. So AI here is producing the tree of all possible atomic nuclei that can occur to not only find, needed end products, but to strengthen current nuclear physics models. And so you can kind of draw in some similarities between how AI might help here and how AI helps in other things like chess. Chess is the main place where AI kind of helps in the same way that it does here. It maps out all the possibilities of a given chess position and The fact that AI is doing this for astrophysics as well in a similar ways, I find to be quite amusing, quite interesting. And it's always nice to hear about ways that AI can be positive because there's always this concern that AI is being misused in certain ways. So with that, let's get into our last story of the day. And it's one where we come across a familiar celestial phenomena. If you were around for episode 9, we talked about the brightest gamma ray burst ever recorded. If you remember that, you'll also remember me making fun of the fact that they branded it the boat, brightest of all time, which just sounded like a ridiculous Gen Z type acronym for such a unique phenomena. Unfortunately for me, the name is here to stay because a plethora of articles have just came out describing the origins of the boat, and they just won't stop calling it boat, so I guess I'm just gonna have to roll with the name. It's the boat. But yeah, lots of articles about some news that's come out about it, and it just sounds so ridiculous saying boat. Like, I mean, it's better than the way that astronomers usually name gamma ray bursts. Like, they'll have like GRB and a bunch of other numbers after it, representing the date that it was observed. So I guess the boat is better than that, but I don't know, I just don't like calling it the boat. But we're gonna call it the boat because no other better name. So the news is that we know where it came from. It was because of the collapse of a star, which sounds kind of lame at first, but let me, explain it. Just give me a second here. Let me cook. Astronomers believe it was a supernova event, but supernova events like this were predicted to produce heavy elements like platinum and gold, and there was no sign of these elements in the aftermath of the explosion, because astronomers expected the R process to occur in the surrounding environment, and we just talked about that. But it turns out it did not happen, and massive supernova likely won't be the origin of heavy elements. So that's a nice addition to the previous story. I quite like how it integrates this article integrates itself with the previous one. So that's the fact of the matter. But there's also some other stuff. The supernova that produced the explosion wasn't super luminous itself. The leading theory for why this is because powerful jets of plasma were released in the event that would have created a more concentrated light source than the supernova itself. I think it was just a regular core collapse supernova, but here we have a quote where they actually describe this whole leading theory. Quote, team member and University of Utah assistant professor of physics Tamoy Lasker thinks the extreme GRB could be a result of the shape and structure of near light speed jets launched by collapsing massive stars as they create black holes. If a massive star is rapidly spinning when it collapses, then the beams it blasts out are narrow, then more focused and thus brighter. So that's kind of the hypothesis here. And it would give us a valid reason for the unusual brightness of the gamma ray, which I believe they had to wait 6 months after the burst to be able to observe what's actually happening at the source, which is quite wild, and it tells you just the magnitude of the luminosity that we're talking about here. So that's what we know about the supernova and how it could have possibly caused the gamma ray burst. What is left of the explosion is probably a black hole, as would be the case with any other core collapse supernova. But one thing I do want to add that was mentioned in the article in this following quote: in addition to learning more about the boat and confirming its origins with the JWST, the team was also able to detect the signature of an intense bout of star formation in the event's host galaxy. This indicated the star that died to birth the boat may have formed in a different environment than other supernova stars. So yeah, just a sort of a bigger picture thing, like we might be able to learn about the composition of this star compared to its peers and what that region of space looks like. So yeah, that's what I've got for the boat, as they call it, and for this episode here. If you all enjoyed listening to this episode, I would sincerely appreciate a subscribe here on YouTube. And if you stuck around here on YouTube but plan to listen to these podcast episodes on Spotify, you can go ahead and go to Spotify, drop me a follow there. It'll be under, Ephemeris Podcast, same name as on YouTube. And until the next episode, I will see you all later. Peace.